pero si tenía la opción de ponerlo normal. ¿Qué?
O sea, es que este está ahí.
Opción, es el calendario de, no sé. No puede ver.
Pensé que imágenes. Lo que yo me acuerdo. Pues no pasa nada, no tendría que pagar. No es el viernes, ¿verdad? Que realmente el 16. Pero del 16 al 27 hasta el 25, pero
entonces siempre son como 15 días, 15 días versus 3.
Natalia, has visto que he movido todo lo que he podido y que era el 5 de diciembre. Lo hice, lo tuve y.
Hoy es 5.
Yo tenía que haber pasado por el bloque 16, tenía que haber tenido los normales. Hice todo lo que estaba en el alcance.
No, pero entonces no estoy molestando.
What's happening?
HDMI.
HDMI should be so.
Yeah, that's right.
O sea, yo invoqué. Me piden como un montón.
Ahí fue mal.
Is that good?
I don't think so. Yeah.
All the planets.
Sorry, planets. Yeah, we're good.
Okay. Yes. Get started. Oh, sorry. Are you ready to go? Yeah. Okay. Hi, everyone. Yeah, I hope you had a good lunch break. We're going to continue with the next part of our lectures. Now talk about interferometry and in particular how to use ALMA in interferometry. So the contents are, I'll briefly reintroduce ALMA. I mentioned it briefly this morning. The basics of interferometry and then also ALMA interferometry, so essentially what part of all these equations do you actually need. I'll go over the calibration process, the cleaning or imaging, how you make images out of ALMA data. Some basics on CASA inspection, like how can you inspect data before imaging it. Continuum versus line, detections, non-detections, and using the ALMA archive. After that, we're going to do a tutorial, but I'll comment on it after. And yeah, please stop me in like 45 minutes or so to have a break. So I don't really have a natural break point in this slide, so I just try to keep an eye on it. Okay, so ALMA, I will be Atacama large millimeter sub-millimeter array, located in Chile. It's an array of 66 antennas in the Atacama Desert at more than 5,000 meters elevation. Started operations in 2011. It's operated and built by collaboration between Europe, North America, Chile, and East Asia. So they all have contributed to the funding and also the continued operations and support of the telescope, and all astronomers living in these countries can apply for observing time, but there's also a fraction of open time for the rest of the world, including Colombia. At least there's no collaboration between ESO and Colombia, right? Not yet. But you can also always collaborate with people in these countries. So the budget of ALMA was, this is a number I always quote, but maybe it has increased by now, $1.3 billion for operation of 30 years. So it's kind of the same amount as for a space mission. It's really a very expensive project, but for a lifetime of 30 years, hopefully that will be worth it. Sensitivity is 100 times higher and resolution 200 times better than previous interferometers, so there's an enormous increase in what it can do compared to other arrays that I showed you this morning. And resolution, I should have fixed that. Resolution can actually go down to 0.001 arcsec. ALMA itself actually consists of 3 arrays, so 66 antennas is the total, but there's the 12-meter array, so this refers to the diameter of the individual antennas. 12-meter array consists of 50 antennas that can be set in 10 different configurations, so for different baselines and resolutions. Then there's a compact array of 7-meter antennas, those are 12, and finally a total power array for antennas that can be used together as well. In protoplanetary disks, we only use the 12-meter array because that's the one that gives us enough resolution. We don't really, so I'm not really going to talk about the compact array. Honestly, I've never used it. I don't know all the details of it. So the compact array is for observing larger scale structures, like for example molecular clouds. Okay. So ALMA operates in the sub-millimeter millimeter regime, or the sub-terahertz regime. And then in ALMA we often talk about bands, so you will often hear ALMA band 6, ALMA band 3. This always refers to a frequency or wavelength regime where the atmosphere is more transparent than next to it. So let me explain it. So this is a graph of the transmission of the atmosphere in the carbon dioxide at temperature as a function of frequency. At the lower frequencies, the transmission is almost 100%. There are still some deep absorptions here and there. These are other features in the atmosphere. But in between, you have this very high transmission, and that's where the different bands are located. 1 and 2 are actually still being built, but 3 up to 10 are available for observations. As you can see, they're kind of alternating with these absorption bands in between. When we go to the higher frequencies, as you can see, this is where the huge water absorption features are. So even band 8, 9, and 10, they are in between those absorption features, but even there the transmission is actually not that great. So at these high frequencies, you always have to deal with more problems and turbulence from the atmosphere. And so the range is something from 40 to 900 gigahertz, or is that 300 micron up to battery is 3 millimeter, and the range goes up to 9 millimeter. Okay. So why do we want to use interferometry? Say that we have a single dish millimeter telescope, like the JCMT, with a 15-meter diameter. If you calculate the resolution for a single dish 15-meter telescope, you will get a resolution of about 14 arc seconds. So that's way larger than the size of the disk. Also, about that this morning. With an interferometer, we can instead use the baseline, and then for 500 meter baselines, we can go to 0.4, and for 10 kilometers, we can go down to 0.02 arc seconds. So this is the reason to use why we want to use the interferometer. So, what does that actually mean, interferometry? But you may have seen this experiment before, but not with the chip. So this is like a double slit experiment where you shine light through a pinhole and then through 2 double slits, and then you get this fringe pattern on the other side. I have to give credits here to Logan Francis, actually, for all of the slides in this talk, because he has made a lot of very nice visual examples of interferometry here. So what we measure with an interferometer is the Fourier transform of the sky brightness. So if you have an object on the sky, and Fourier transform that, we measure visibility, and then the interferometer measures the signal in digitized samples, so fixed different baselines, and you try to map or to complete that sampling as much as possible by having many different baselines. The samples measured will depend on the antenna separation, but also on the orientation of your object, so basically how high it is in the sky as a function of time, and also on the observing time. So when you measure these visibilities, you then need to do an inverse Fourier transform in order to go back to an image, and this is what we will discuss later on. This is the so-called cleaning or imaging of visibility data. So these are again kind of the fundamentals of an interferometer. There's a lot of math here. I just want to tell you beforehand, don't worry too much if you lose track. You don't actually need to do all the math to work with ALMA data. I just want to explain the basics from this perspective, but again, don't worry if you can't. It also took me several years before I understood all of these nonsense. So if you have a pair of antennas in an interferometer, they're separated by a baseline distance t, observing a source over there at frequency u, direction s. Each antenna collects a signal and converts it to a voltage. So this is now digital electric signal that can be amplified. And this is really important because you want to be able to split the signal to make baselines with different antennas. So this is why the amplification is really important. So you now have this oscillating signal at antenna 1 and at antenna 2, antenna 2 and at antenna 1 you see the same signal but with a certain phase delay because the light arrives there a little bit later. So the signals are digitized and then multiplied with each other. So this is how you get your fringe pattern that we saw also in the double-slit experiment. And then the fringe and the amplitude of these fringes is directly proportional to the brightness of the source. The phase is sensitive to the source position. So this has to do with the light of the source arriving at a different time at the later antenna. This has to do with where the source is located on the sky. And if we now have an extended source, like say something with a lot of rings, your correlator is sensitive to the even components of that. So now we're going to get to all the math. And again, I still get dizzy looking at it, so don't worry. I just wanted to put it in there for convenience. So you want to measure both the even component and the odd component, the cosine and the sine, in order to combine them. Then there's a couple of things you need to be aware of. First, there is the bandwidth. So in an interferometer, you always have a limited bandwidth, a limited frequency range. So if you make the bandwidth too wide, you can imagine that your fringes start to interfere with each other. But because of this, because the bandwidth is finite, you also start to attenuate the amplitude away from the center. So again, these are things to consider, that the bandwidth is actually important for being able to interfere your signal and stuff. When the Earth is rotating, obviously your phase changes as well as a function of time. So you're essentially moving the fringes continuously. And you can solve that by adding some additional delay between the two antennas, and then you can always refer to the phase center, essentially, a reference point for tracking the phases. Then, primary beam. This is not so much an interferometric thing. This is actually something that you may also know from other types of telescopes. Is that your dish is not equally sensitive over the entire surface. So if you're further away from the center, you essentially introduce more noise. So this means that you always need to track your source. You always need to make sure that your source emission arrives in the center of your primary beam. But also, once you are creating an image, you will always see that at the outer edges, your noise level increases. Okay. So let's now talk a little bit more about coordinates. So we like to think of objects in the sky as being these 2D structures, and you can express that in coordinates L and M. Just for you can also say X and Y or right extension definition. But for now we call L and M for east, west, and north, south. And as I mentioned, what you are measuring with the interferometer are the visibilities, and they are measured in the coordinates U and V. So U and V is essentially the Fourier transform of the element. Also the U and V are actually wave numbers. So these are distances in meters divided by the wavelength where you are observing. Okay, so now the Fourier transform itself looks like this. Again, you don't have to do this yourself. But the so this is the function that describes the image. This is the Fourier transform, so this is what you measure, the visibility. And if you had a complete sampling of the visibility, so if you measure all the possible combinations of U and V, you can simply inverse Fourier transform that. Then the opposite is just minus sign. That's the only difference. It's a mathematical operation, but this is only for perfect sampling. In practice, of course, you never have perfect sampling because you just have a number of antennas and a number of fixed points where you take your measurements, and that's going to affect finally in the end the quality of the image. Okay, so how does this look like in terms of that sampling? So we're going to start very simple. Again, first starting from the sort of the double slit experiment. If we have two antennas, two little points, the response of a point source will just look like a sine wave. So if we increase the baseline, you can see the fringes, the sine pattern just becomes more narrow because we're observing it. Essentially, we're able to measure a smaller separation. If we rotate the antennas, your UV sampling also gets rotated, and this is actually something that we can use because the Earth is rotating. So it's not just how the antennas are with respect to each other, like when they're fixed in place, but also while the Earth is rotating, what you see is that you start to cover multiple UV points. This is always basically symmetric, so you always get it both in the center and the center. But rather than having a point, you suddenly have a series of points. And that's, it's not immediately visible, but now when you start to take more and more of the Earth's rotation, you see that fringe pattern starts to become more and more like points, like it starts to look more and more like a point spread. So now we actually have, this is now the beam or the resolution element. This is it represents the sampling of the image in the image space. And like I said, if you know, so far we've just been talking about two antennas and the Earth is rotating. Of course, when you start adding more antennas, you suddenly have more respective relative distances. So now you start to fill up your UV plane by all these different baselines, again as a function of time because the Earth is still rotating. So as you can see, the beam starts to become better and better. So now we have four different antennas. Now we don't really see the fringe pattern anymore. We really see this bright response in the very center and just a little bit of side lobes all around it. This is, again, whatever you're looking at is going to be the result of the structure of your image convolved with that point function. And again, getting even better. So you see, you start to, the more UV coverage you have, now with fat antennas, you start to get rid of your side lobes. There is a frequency dependence here, obviously, because of the lambda over B dependence and the UV being measured in wave numbers. So you can always get better resolution at shorter wavelengths with the same antenna configurations. Okay, so I just wanted to end here with this image. If you're here now, don't worry, then you can also forget everything I just said because you don't. And as soon as you start working with data, this will a lot of this will actually become more clear. Okay. This is actually more of an overview slide. As Esteban was looking at the PDF of this on the website. So you can find all the links there. Interferometry. It's a very deep, complicated topic, in case you weren't convinced of that yet. And there's a lot of material online if you want to read more. So if you're interested in this stuff, again, there's other people who can explain a lot better how all of this works, also from mathematical perspective. This includes some summer schools, some books. These books are also, this book is fully available online. You don't need to pay for it. And then there's of course also the documentation of the online side. Okay, so let's now go to a little bit more practical. So rather than looking at the equation, let's just take a look at how we use this in practice. If we have, and this is, a lot of this is actually about if we Fourier transform our image, like whatever we see in the sky, how does it actually look like in the visibility? So if we have a delta function in the sky, like a point source and a result source, your visibility will be constant. Your visibility signal will be the same at all baselines, because it's infinitely small. Of course, nothing is really that small, but it will approach. A Gaussian, which is a little bit larger, will look like a Gaussian, will also look like a Gaussian. But then you can imagine that the smaller you make this Gaussian, the larger the Fourier transform Gaussian will be. Until eventually this Gaussian approaches the delta function, and then that Gaussian approaches constant. So again, visibility becomes constant and as a function of the V distance. And at some point you can just, you know that you can no longer resolve it. If we start to think a bit more about shapes or morphologies, then an elliptical Gaussian also becomes an elliptical Gaussian, but then rotated. That is clear based on the UV plots I was showing before. And a disk, and this is called a disk, but it's actually just a circle with sharp edges. That becomes a so-called Bessel function. And the reason that you see this ringing pattern, so that it essentially goes up and down, and down, and down, that is mostly because of these sharp edges. So you can imagine that at longer UV distances, you get these variations in how quickly the signal changes. And that keeps going. So this is Fourier transform of a sharp circle is a Bessel function. Okay, so as I mentioned, the key thing of interferometry is that you want to sample your UV plane as good as possible. So at each of these combinations of U and V distance, you want to have an antenna, and then you want to rotate with the Earth. So what you see here is really the UV coverage of a telescope as a function of time. And you can even see that there's this double pattern. That's actually because of the two polarizations that the telescope measures. That's not something we usually worry about. We usually just combine those two. But that's why you have a double pattern. The second thing that you see is that it's like a line and then a gap, a line and a gap. So this has to do with calibration. You do your science observation, but then every now and then you have to go to the calibrator. And then you go back to your science start, the calibrator science start. Come back to that as well. Okay, then in each position in that UV plot, as a function of time, you measure your visibility, which is a complex signal. So a complex signal as a real part and an imaginary part. So you may have heard of this with complex dynamics. What's important there is that the real part, that sounds really strange in the paper, it represents radial variations. So whatever changes in the radial direction in your disk, for example, if there's a gap, that's going to have an impact on how your real curve looks like. The imaginary part represents azimuthal variations or phase variations. So this is mostly important if you have an instrumental piece. Then You can also, instead of looking at these separate visibilities, you can combine them in amplitude. That's the square root of real squared plus imaginary squared. All the software calculates this for you automatically. And you have your baseline in one direction is essentially u squared plus v squared again square root. So in that case, you have your visibility not as a 2D plot, but as a 1D. Yeah, I have some examples of that here. So here we're always just looking at the amplitude signal as a function of UV distance. And if you remember that image from the Bessel function, you hopefully recognize that this is the exact same pattern. So we have something very bright in the center, goes down to 0, goes back up again. So this, in 2 dimensions, just looks like that ringing pattern. Then we remember the Gaussian image, that in 1 dimension looks like a Gaussian curve. And for a constant, I didn't really have a good example of that because almost everything we observe is that in terms of this is somewhat resolved at least. But what you would see is that it would remain constant for a long time. Only if you go to very, very long baselines, so it's going to be very, very high resolution, you will start to resolve your source, and that's why this signal will go down. So hopefully this gives you a bit of an idea of looking at a visibility curve. What does that mean? Like, this is the Fourier space. What does that mean for your image? And yeah, 2 of the major issues when Fourier transforming a visibility are the maximum resolvable scale. Just kind of the maximum scale that is covered by your data. Because say that you didn't have these short baselines, right? You only have this part. That means that you don't know the total flux of your source. You don't see, and you will not be able to recover the large-scale emission in your image. You only have this rapidly varying patterns. So in that case, in your image, you will not be able to recover for this. So I'll show an example. The second, incomplete PSF, that is again incomplete UV coverage, which can lead to these strange imaging artifacts. Okay. So in connection with ALMA, I will give you these basic numbers before 12 meter array 50 antennas. So you have to remember here that each antenna is connected with each antenna. So there are lots of cables underground that connect all these different telescopes, and so that connect all these different antennas. And it also means that the number of baselines that you have grows exponentially. So if you have 3 antennas, you have 6 baselines. If you have 4 antennas, you have 24 baselines, etc., etc. ALMA itself has, I don't know, thousands or even tens of thousands of baselines. Each baseline provides a resolution element at a certain point of time on a spatial scale of lambda over the baseline length. So that's a point of the UV plane. And if you want to make a nice image, you want to fill out the UV plane as much as possible to cover all these different spatial scales. I'm going to show examples of what happens if you don't cover them properly. So this again just some terminology. UV plane is for instance from the XY plane or the LM plane. The sampling of UV plane, the better it's filled, the more accurate your image will be. And this is something where ALMA also made a huge improvement. So this is the UV coverage of the SMA, of I think a 6-hour observation. This is UV coverage of ALMA for 1-hour observation. You can immediately see that the UV coverage of ALMA is much better, that your image fidelity is actually will be much better. The Fourier transform of that UV coverage, that gives you your beam element. So that essentially tells you how many side lobes or weird artifacts you're going to have. So if this is constant, you're going to have a perfect beam. Of course, it's never completely constant. You can see that here as well. It looks kind of black, but there's still some gaps here and there in between. So you will always have a little bit of refractance. And another thing to remember here is that if you have good coverage at long baselines, so if you're in an extended configuration, that means you're sensitive to very small scale variations. Short baselines, you're sensitive to large spatial scales. But there is a limit to the combination of the longest baseline and the shortest baseline within one configuration. So you either need to combine two configurations or accept that you don't trace both scales at the same time. And that last thing that is, you can kind of visualize this here. This is the table that you can find in the ALMA documentation. And it is essentially listing all the configurations. And then for each band, it shows you AR, the angular resolution, and MRS, the maximum recoverable scale. So, say that we, so these are the baselines ranging from, in configuration 1, 15 meters to 160 meters. These are the range of baselines, and it means that, let's say at band 6, we can observe something with a resolution of 1.5 arcsecond, but the maximum scale that we cover is 12 arcseconds. So, for quantiplanetary disk, this is not an issue because they're way smaller than this. So let's go to a bit higher angular resolution. Let's say, let's go to the very bottom here. We have band 8. We go configuration 6. We now go up to 2.5 kilometer baselines. That means that we have a resolution of 0.07 arcseconds. But the largest scale we can cover is only 0.9. So if the disk is larger than that, we will essentially miss part of our image. So a little bit about that, about the UV coverage. These are examples mostly from SMA because it's just easier to visualize in that way because all my UV coverage is so good. If you have like a short observation with the SMA with 8 antennas, this is how your PSF is going to look like. You have something bright in the center, but there are many smaller copies, many side lobes kind of all over. And this is what we call the dirty beam. It's the Fourier transform of the UV coverage. If we start to fill the UV plane, things get better. We now have the dirty beam, like we still have. We definitely have a bright Gaussian in the center, but we also see that there are all these sort of side lobes, so whatever image you're going to make, you may see these artifacts throughout the image. Only if we have a perfect uniform coverage, we can get to a perfect beam without any side lobes. So I'm going to show you basically what happens if you do not take into account that UV coverage issue. And I'm going to do this using an ALMA simulation that I've done. So I'm going to provide an image and put it through the ALMA simulator. The ALMA simulator calculates what the image would look like with a given configuration, based on a given list of parameters, like how long do I want to observe. And so this is UV coverage of our observation. So and here's the example. So here we have our model image. This is what we're going to feed into the simulator. We're going to observe it with configuration 5, which has an angular resolution of 0.1 and MRS of 1.2. And now we're going to take a look at the difference between the convolved image and the simulated image. Because convolved, that is something that you do, then you're essentially just blurring your image with a beam size, right? We know our resolution, and it's going to make the image a little bit blurry, but otherwise we're not actually going to lose any information. And as you can see with this sort of relatively low angular resolution, the difference between convolved and simulated is almost non-existent. This pretty much look the same. Because that tells us that the UV coverage is pretty good for this configuration and for this size of the disk. However, if we go to configuration 8, 5 times higher angular resolution, so our convolved image looks pretty good, right? That almost looks like our model image, it's just like a little bit blurry. But if we now go to our simulated image, and this is what Alma actually would observe, we barely detect the signal because we're missing the short baselines, we're missing the large spatial scales. What we see are the small scale spatial variations. So you see here, there's this variation on very small scales. That is what is recovered. But you don't really get the large underlying ring structure. And in fact, if you measure the total flux here, you will find that you only recover about 1/3 of the total flux. Well, in this case, you will recover. Another example of UV coverage, because again, this is one of the most crucial things to understand about interferometry, and it's not very intuitive. And this is again an example from low winters I really like. So say that you observe a pineapple with almond. And if you do that with a UV distance like with short baselines, you essentially get the main shape of the pineapple, right? But let's now observe it in an extended configuration. Now we can see that, you know, that diamond pattern on the pineapple. We can see those little substructures. We can see the lines throughout the pineapple and maybe some of the lines here of the leaves. But we're missing that large scale, the overall, that covers the overall structure, that gives it the appearance of a disc. Okay. One final example. Yeah, sorry, I had a lot of examples, so I figured I'm just going to show all of them. So you can take a picture of Einstein and so again put it through the ALMA simulator. This is with sort of intermediate configuration resolution 0.2, so we get kind of blurry Einstein. Then we go to a very compact configuration. Now we just see like that it's sort of circular. It's like a head. You don't really recognize him anymore. And now we go to a very extended configuration, where again, what we see are the small scale variations. We just see the lines, we see the eyes maybe, and the chin here, but we're missing that large scale structure. And just to show you again the difference with convolution, if I had simply convolved my image with a 0.03 arcsecond beam, it would look like this. It would just be, you know, somewhat blurry Einstein. The interferometry is not going to give you this. It's not going to give you this if you only observe it with these long baselines. So I hope that clarifies things a little bit. When you are looking at an ALMA image, you always have to check, am I covering all of the emission that's really there? Okay, then, I already mentioned that with ALMA, we're observing in a millimeter with a square X regime. And then you may sometimes hear these terms, a lower sideband and upper sideband. And this has to do with this bandwidth problem, that you cannot, that you have to keep pretty narrow bandwidths in order to interfere the signal with itself. And you can do that on both sides of your central frequency, the local oscillator. In each sideband, you can set multiple spectral windows. So a spectral window is essentially a small frequency range, let's say from 345 to 346 gigahertz. And that's the coverage of your one spectral window. And here you see some, if you were doing this within the ALMA software, you can actually overplot what molecular lines are visible in that frequency range. So the reason why we need to have that upper sideband and lower sideband is this local oscillator. It is a bit of a trick that we have to use. because a 300 gigahertz signal, that's varying really rapidly. And in order to transport that through an electronic system, that's pretty complicated. So you kind of want to downscale the frequency, but maintain where the frequency actually originates. So if you mix a high frequency signal with another high frequency signal that is just a little bit shifted from it, what you are left with is just that difference. So say you mix 345 gigahertz signal with a 340 gigahertz, you're left with a 5 gigahertz. And this is something that you can now put through your electronic cables, interfere with the signal from other telescopes, and essentially create your interferences. This means that the upper and lower sidebands are limited to essentially the 4 to 8 gigahertz from your local oscillator on either side. So your upper and lower sideband are maximum are between 8 and 16 gigahertz away from each other. You cannot go further than that. This is mostly to explain why you have certain combinations of spectral windows in all observations. I don't know who's playing music.
Sorry.
Who's playing music? Is that outside?
It's outside.
Okay.
Yes, yes.
I know. I wanted to
Who was playing music?
I didn't want to call you out.
It's not music. No, it's outside for sure. It's a radio station.
Oh, okay.
It's Olympica.
Yeah. So then within ALMA there's some difference between the band 9 receivers and all the other receivers, just in case you would ever work with them, that you can set up your spectral windows a little bit. So then this is how that looks like in practice. So you see you have your lower sideband and your upper sideband. Then within each sideband you can set your spectral window. Here you see the four spectral windows that you can choose at the time of your observations. And a spectral window contains 3,840 channels. So you can choose to either use a broad spectral window with low velocity resolution, so essentially if you want a wide continuum bandwidth, you want a high continuum sensitivity, or a narrow spectral window where you go for very high velocity resolution. So you have to remember that you always have the same amount of channels, but you can choose what velocity resolution each channel is before you make some of your observations. This actually depends on your science. If you want to do something with kinematics, you always want to go for a very high velocity resolution, but that means that you lose continuum bandwidth. But if you are mostly interested in observing continuum and you don't really care about the lines, then you go for something broader. In practice, most people choose something in between. So, again, if you want to hear about the different choices in different ALMA data sets, this is pretty nice. Let's see, but then finally this is a very detailed comment. So when you set your spectral windows, you set it in principle at the rest frequency of your wavelength line, the frequency of your line. But because the Earth is rotating, the Earth velocity is actually going to change that frequency a little bit. So if you were to look at an ALMA observation, you look really at the numbers of those frequencies, you may see slightly different numbers every time. Sometimes if you combine two observations, they also have slightly different numbers. It is because of the Earth velocity being different at different times of observations. So it's again, you don't have to worry about it. The software takes care of it, but this is mostly if you really worry about these numbers. Okay. Let me pause here for a moment. Is this more or less clear? Do you have some idea of this is what the interferometer can do? This is what spectral windows are, because we're going to get to the imaging part for now, I'm going to switch gears a little bit. Any questions at this point about interferometry?
I have a question maybe more regarding how do you choose between the baselines? But you already told us that it depends on the science.
It depends on the science. So if you want to observe something at really high resolution, you have to make sure that your object is not too large. And if it is too large, then you have to observe two configurations and combine those two outputs.
So, and the image you showed us, it's maybe like, can be related to the beam of an antenna or something like that. Like all the baselines we draw with all the lines, something like the beam of our.
So the UV coverage is the Fourier transform of your beam. So if your UV coverage is 4, if the sampling of UV coverage is 4, then your beam is going to be massive. Well, if your UV coverage is very well sampled, if it's almost uniformly sampled, then you get a perfect Gaussian beam with no side. So then,
That's what we are looking at.
That's essentially what we're looking at. And it's really hard to think in Fourier space. So that's why I'm trying to give many examples to hopefully give you a little bit. Okay. So then I want to switch to calibration. Maybe I can start with a question there first. Why do we need calibration in astronomical observations? What is calibration?
This is roughly what ground?
Sorry?
It's roughly what ground? I mean,
Yeah.
remove it.
Well, if I like say in optical astronomy, if I have to do photometric calibration, what does that mean? Flux calibration.
To know the intensity of the signal and in relation with my ground or foreground instrument.
Yes. Yeah. Exactly. So calibration is something that you need to do in order to convert your signal to essentially meaningful physical parameters. If I say the star is 10 magnitudes, I can only do that because I count photons and I compare that with a star that I already know, for which I already know the parameters. So I know exactly how many photons are how many electrons are produced by my detector by a certain star. But in all my interferometry, we have to do the same thing. We have to consider the fact that my instrument changes in response as a function of time. On top of that, we have atmosphere, we have a number of other things that change with time that will affect the measurements. In particular, if we do consider that we do measurements on multiple days, or like we do an observation that was done a year ago, but now we do it at a different configuration. We always have to check if we're scaling things properly with each other. Because what we measure are amplitudes and phases of sources. It's essential as a function of time. But then there are all these disturbers that change with time as well, like weather, atmospheric transmission, antenna response, instrument response. So essentially, how the signal, the signal that goes in and the signal that goes out, that can change as a function of time, as a function of whatever earthquake or sandstorm happened at the moment. All of these things you need to take into account. It means that we need to calibrate each antenna all the time. Literally during an observation, we need to constantly check that we are converting our electric signals to physical signals of our source. That we do that consistently in the same way. Otherwise, we can never use multiple data sets to combine data or compare data with the previous measurements. So all my calibration is in principle done for you when you are taking observations. So it's not something you really have to worry about, like how are we going to design these observations. But I do want to go through the basics of like, what kind of calibration we need to do. So there are observatory calibrations, which are only done when antennas are moved from one configuration to the other. So this is the making sure that we know the exact position of each antenna in the array, because of course that sets the baseline length. Right? The focus and pointing of each antenna, because we want to make sure that we know exactly what we are pointing at, that the coordinates that we put in our computer, that is also what the telescope is doing. Surface accuracy and primary beam pattern, same thing. These are properties from each individual antenna that can be affected when we move an antenna from one configuration to the next. And this is essentially done every time when the antennas are moved. Then there are a number of calibrations that are done for each ALMA observation. So we're going to go through them one by one. There are a lot, but again, most of it's not something you have to worry about when you're doing imaging. So first of all, yeah, this is not so much. This is essentially a check of things being broken during the observation. Like broken antennas, broken correlators, shattering of telescopes, radio frequency interference, so essentially other signals going around. There could be spikes in your data as a result of any of these glitches. In that case, we cannot calibrate for that. We just have to get rid of that piece of the data. We try to do that as little as possible, like only for a small frequency range, only for a small amount of time of your total observations. And essentially, when I say we get rid of data, we flag data. That means it's no longer used in the image. Then the system temperature is essentially all the noise due to microwave electric backgrounds, atmospheric emission, losses in feed, ground radiation, receiver noise temperature. So this is more like an intrinsic property of your receiver, of your antenna, again as a function of time. When that noise goes up, we want to downweigh that part of the data. So again, if we have 2 hours of data, and the first 15 minutes we had a lot of this kind of noisy emission, we don't want to throw away those 15 minutes. We just want to make sure that it is included less in combining all the data together. Say we have 15 minutes, so let's say we're only going to use that for like 5% of the time. And this is this also become clear with the team. So in order to check whether any of these noisy things are happening, we often measure hot and cold loads. So these are just like little electronics in each antenna, and sky contribution again as a function of time, just to make sure that they're constant. If they do change, then that is a way to that's a reason to say, okay, this part of our observational time, things were not acting the way that they should. So that's not worry too much about the data during that point of time. Water vapor. So the water vapor in the atmosphere causes changes in the phases. So you can imagine that whatever signal and whatever phase change is going to affect your experimental signal. In order to correct for that, there are these little radiometers on each antenna that measure the amount of water vapor along the line of sight constantly. And it actually tracks whenever the amount of water vapor is changing, and also there it can kind of correct and change the weights of the data that is taken in particularly bad circumstances. So now we get to the calibration on the science observation itself. This is actually, these are the things that you may have to deal with in practice sometimes, that this you recognize. I already mentioned you have to do flux calibration, so you want to know what your electric signal, what that corresponds to in terms of your radio signal. You have a bandpass calibration, so this is kind of the same thing, but then as a function of frequency. So if your sensitivity is higher at your higher frequency spectral window than at your lower frequency, you want to know that beforehand so you can scale it. Again, this can simply happen as a result of temperature or some problems. So these are things you measure basically every hour during observations. Or every 1.5 hours. Then you have your actual science observation, and I already mentioned this earlier on. During your science observations, you want to measure the phase of your atmosphere continuously. And you have to do that regularly, so essentially you observe your science target for, let's say, 10 minutes, and then for 2 minutes you go to your gain calibrator to measure the phase of the atmosphere. And then you go back to science, and then 10 minutes later you go again, measure the phase of the atmosphere. If the phase change, you can interpolate between that and correct for it for your science. This is what the gain calibrator does. So, what are sources for flux calibration? So here, there is so you want to observe something that you know, for which you know exactly how bright it is in other units. And sort of the first option, so this was done with sort of previous interferometers and also early on nowadays. Use solar system bodies, so in particular moons around other planets in the solar system, maybe some asteroids. And the reason for that is that the fluxes of these objects are known very well. Like we know exactly what the orbits are, we know how far away they are from the Earth at all time, and we know exactly how bright they are. The problem is that, well, first of all, so they all orbit the sun, and we orbit the sun, so not everything is observable at all times. And the second problem is that they are actually not that small. Which means you start to resolve them, and remember what happens if you resolve something, it becomes this Bessel function. So it means that at some baselines, you essentially have zero signal. And that means that if you apply that as a flux calibration, you get very noisy data at some of the baselines. This starts to become very messy at high angular resolution because your signal becomes so low. So what you actually want is something that is constant with baseline, which is a point source. So a possible point source is a so-called quasar. So this is a radio source. These are mostly galaxies that are pretty far away. You can find them all over the sky, pretty bright. Problem with quasars is that they are actually variable with time. But the flux varies with time. They're not constant like solar system planets and moons. So for those, we again need to monitor the size calibrators, not every 10 minutes, but at least every few days, to make sure that they don't vary. And then again, compare that with something that is more constant, like something like solar system. So there's still a bit of debate about how useful this quasar flux calibration is. It's just something to be aware of. If you measure a flux that is very different than what you expect it to be, it could be because that quasar started to do weird things and it wasn't properly monitored at that time. Okay, then the bandpass calibration, I already mentioned that your sensitivity can change a little bit across a spectral window. And here you see call this the amplitude as a function of channel, so as a function of frequency. You see that over here the response is around 1.02, and here it goes down to 0.95. So you say that you want to make sure that everything is weighted equally, that you correct for that sensitivity that is slightly different on the other. And then finally, this gain calibration. As I mentioned, we do this every time in between science observations. So here we just have an example. So say that the phase varies as a function of time according to this dotted curve, right? So it's going up and down, it changes a little bit. We measure the phase just before our sun-starting observations, and we measure it afterwards. And then we can see that the phase changes, and we interpolate it usually by just drawing a straight line. Yeah, this is simply the best we can do. We cannot measure the phase continuously. We can only measure it every now and then we just hope that it doesn't change too much on top of that in between. Okay, so this was the calibration part. So after essentially all of these calibrations have been applied, we now have visibility data that are as good as possible and that are in the right scales and units, etc. Now we want to Fourier transform our visibility data to an image. And maybe this is actually a good time to take a break because it's 3 o'clock. So let's take a 10-minute break and then we'll continue.
How long do you think we should take this break for?
10 minutes.
The thing is that we have a problem with coffee because they closed down the store.
Oh, okay.
So we were thinking that we should maybe let them have a longish coffee break so they can get coffee.
Then maybe we'll do a shorter break and then before we start the tutorial, then let's have a longer break.
Ah, yeah, okay. Yeah,
So then
let's do that.
maybe now just keep it short because I'm still in the middle of the lecture.
Sure.
Yeah, I have a question.
Yes.
I know that you said about this subdivision.
Yes.
Right? But what it means, because well, it's in my prepared now, so I want
Okay.
to
No, I understand.
Yeah.
I was actually not going to discuss it, so but it is actually illustrated in this. So if we correct the phase by measuring the phase at this point and at this point, all we can do is draw a line. But the real phase changes during the science calibration. Self-calibration means that you try to measure the phase from the science target itself.
Okay.
So you can only do this if the science target is very bright.
Okay.
And you have to be, it's something that you have to be careful with because you can, if you do it in the wrong way, you can completely mess up your image, create artifacts.
Yeah, in that way they just made one.
They say we do self-calibration, that it means that they correct additionally for phases. It always, the idea of it is, of course, that it has to lead to a better image, a better signal to noise, because you get rid of some of its phase variations.
Okay.
Yeah?
Yeah. Thank you.
No problem.
Hay otras imágenes que sus datos pueden sí, sí, pero al final es medio ambiguo y de hecho más técnicas hacen lo que se llama concurso de sí, cuando ponen distintos servicios y pero eso this break was short, but we'll have a longer break later in about half an hour.
List of the artists that you passed today, so I can choose the one for my student.
Yes.
Because I have the list, usually you share the exam, but I need to know which ones are the titles of the others.
Y antes de empezar lo siguiente, hacemos un break and you alto está.
It's okay.
Can I do it later?
Mañana sí ya organizado, hoy no está lesionado.
Can you? Yeah, thanks. Okay, so we're going to get to the fun part, the sort of practical part. So I've talked a lot about interferometry and calibration and all the difficult parts and kind of the things we need to be aware of before we start imaging our data, before we start transforming our data. And what's interesting is that imaging we actually call cleaning. Do you have an idea why it's called cleaning and not just imaging? What do we need to clean?
Removing noise.
Not so much noise.
Removing some features.
Yeah, removing the side lobes as much as possible in our PSM. And those side lobes essentially will produce noise kind of all over the image because every signal gets convolved with that beam with all the side lobes. So we talked a little bit about this before, the sampling of the UV plane. So the sampling is not 100%, it's like we cover part of the UV plane, and that means that whatever you Fourier transform is a Fourier transform of the sampling in combination with the image. What we want to get is only the image. So the image, the Fourier transform of that signal is called the dirty image. This is where the cleaning comes from. It's because it's the image in the sky convolved with a dirty beam with side lobes. And this is kind of how that looks like. So we've seen this example before. We have a dirty beam, so it's like there's a bright Gaussian here in the center, but there's lots of little wiggles everywhere. This is the result of this UV coverage. So UV coverage with non-ideal sampling. So if we now image a disk that looks like this, a bit of a ring, and we convolve it with that dirty beam, it's going to look like this, a dirty image. You see, so it's you're convolving it with the beam, so things get stretched out a little bit, but that's fine. But you also get this whole cross structure, and that's the result of that dirty beam here. This is a very exaggerated result, but also in ALMA, small effects in the dirty beam can create fake signal in your image. And since we're often trying to look for very small signals, like say of a circumplanetary disk in a protoplanetary disk, we have to make sure that at least our image is as clean as possible, that we have a very clean beam before we make our image. And so this is another example. Again, this is our original map. This is our dirty beam, dirty map based on this sampled possibility. Okay. Sorry, I think this. Actually, I've done this in a different order. Oh yeah, so the unit that we use for those of you who don't know radio astronomy is Jansky. Image units are usually Jansky per beam because everything is convolved with this beam. The beam is this Gaussian angle of the telescope point spread function. And we can calculate the total flux by integrating all of this Jansky per beam by adding that up over the entire extent of the source. Maybe I'll come back to this later. So what is this beam? I already mentioned this is a dirty beam. We have this center, we have these side lobes. If we take a cut through that, this is how it looks like, a very bright central source and side lobes. And we're now we're going to clean that while also Fourier transforming our data. So this is actually a combined step where we're going to get rid of the side lobes, but at the same time we're going to find a way to find the best possible beam for our data. And to find the best possible beam, this has to do again with how our image looks like. Because remember we have all these visibilities, long baseline, short baselines. And you can imagine that at the longest baselines, there's not that many antennas that are participating in that. That's only the ones that are furthest away from each other. So your sensitivity, your signal to noise on those longest baselines is smaller than at short baselines, where you have many more combinations. So what you do when you make an image is that you weigh the data depending on that coverage. And natural weighting, you essentially take into account that you have less coverage as long baselines or short baselines. So essentially you give more weight to the short baselines. So you always end up with a larger beam, but better signal to noise. So this is called natural weighting. Larger beam, higher sensitivity. It's really suitable for low signal data. We can also do uniform weighting. So there we say, oh, everything along baselines, short baselines, I don't care that the long baselines, that the short baselines are better covered. We're just going to give them all the same weight. In that way, you're obviously going to get a smaller beam. But your sensitivity is also, your noise levels are also going to get worse because we're suddenly adding all this noise from the longer baselines. So you will always have to find a compromise between resolution and signal to noise by the choice of your weighting. This is kind of the key parameter that you have to play with when you're making an image of your data. You choose natural or uniform, or you choose essentially Briggs weighting, where you can set another parameter to a certain value, where +2 equals natural, -2 equals uniform. We usually do 0.5 as something in between, 0.0 or 0.5. And then you're kind of in between. And then you have more extremes of that, and then you do tapering, where you actually get rid of your longest baselines altogether, or you do super uniform, where essentially you use the long baseline data even more, so you get even higher angular resolution, but you lose even more signal. But it's not, you have to be really careful with doing that. This is an example of how that looks like for different weighting schemes. So say we have an image, we use the weights, so our choice of the weighting scheme in that sampling function. For natural weighting, this is how our PSI looks like, and this is our observation. So we have 3 bright sources, they're somewhat extended, but overall the signal is not spreading. So if we now go to uniform weighting, you can see the liquid PSF, the beam, is a lot smaller. So your individual sources become smaller too, they're still in the result, but also things become a little bit more noisy. Then the robust is kind of in between. And we can even go for tapered uniform. So, okay, and that's, I don't know quite really tapered, I would do tapered natural, but okay. So now in this case, we are essentially getting rid of some of our longest baselines. So we get, again, an even larger PSF, but still some of, what am I saying? As you can see, you get a different outcome depending on the wind is scheme. And then it depends on what kind of science you want to do. If you care mostly about resolving structure, or in this case, finding how small my object really is, you want to go to uniform, or like low robust values. If you only care about detecting something, if you don't care about resolving it, then natural weighting is better, because you always have a better signal to noise in that case. So yeah, sorry, I kind of went through this. These are more the formal definitions of the weighting scheme. So I'm just going to skip over this because it's more math. Tapering. Okay. So now we're going to go back to the cleaning. So you need to make your choice for your weighting, and now we're going to go clean. The clean algorithm attempts to deconvolve, so to Fourier transform your image, and remove the effects of the dirty beam. So this is my original dirty image that we saw before, and if we do cleaning, we may end up with an image that looks like this. So it's still convolved, it's still not as sharp as my model, but we got rid of all these weird side lobes everywhere. And the way that the algorithm works is actually, it's summarized in these different steps, but again, the software takes care of it. So you produce an initial image, the algorithm finds the brightest points, and you can help the algorithm by saying, like, this part of the image, this is real emission, so these are where you have to look for your brightest points. Then the software will calculate the brightest points convolved with this dirty beam, and then subtract it from your image. And then you basically start to repeat that process while you keep your residuals every single time, so you know what part is the result of these side lobes, like what part of the side lobes, and what part is actually real. And finally, you're left with a clean model, so this is the collection of all these bright point sources that you found in the beginning. You involve that with a clean beam, which is a Gaussian fit to your dirty beam. So this sounds very complicated, but you will see in practice it actually works really naturally. So essentially, this is the example that I want to show. So we have our dirty image, and this is our difference image. So this is the difference between our dirty image and that model, the brightness points convolved with the dirty beam. And so we have now. So when we repeat that number of times, we're left with this final model image involved in the beam, but then we still have to add up the residuals from that cleaning process. So cleaning is usually done, so we can do now with CASA. CASA is the software that Alma uses. It's also used for the calibration. I asked actually to email you to download CASA beforehand. There are many versions of CASA available. It's usually smartest to go for the latest version, more stable. Sometimes if you reduce a very old data set, you have to go back to the original CASA version, but try to avoid that if possible. Okay, so this is how CASA looks like. So CASA is run in the terminal. So you just have, you just get a point if you start it, and then you can type your commands in the terminal. And all the tasks that you want to do are kind of scripted as Python functions. So say that a task is usually something like the name of the task, and then in between brackets you give the parameters for that task. If you set imp and then task name, it will list all the possible parameters that you can set for that task. You can also do help or documentation to get more information about that. And if you do an if, you can also set each of your parameters individually, and then finally when you fill in all these parameters, you type go, and then it will run it with the parameters that are set. Another thing you can do is tget of the task, and then it will use the inputs that you used the last time that you run that task. So these are just a couple of interesting, of useful tasks. And then finally there's the exec file, so if you have a script that contains a number of tasks, exec file will be the script name, and then it will execute everything that's in that text. Okay, so this is what happens if you do an int of clean. So as I mentioned, it will then list all the possible parameters that you can set in the cleaning algorithm. And there are many, many things that you can set. Most of them you don't need to change. Only a handful. So we'll come to that with the cleaning example. So most of these parameters can be done with default. So these are the things that you usually want to change. Vis, so that's the visibility file that you want to use. Fields, because a visibility file often contains multiple targets, multiple fields, so you want to set the number of the target you want to clean. Maybe spectral window, but if you leave that default, it will just merge everything together. Data column. So this is let's see if I can explain that. So data column is by default always set to correct, but you usually have to set it to data. But it will tell you that is the case. Then in size and cell, these are the default values are not really appropriate for particular things. So in size is the number of pixels in your final image. And cell is the pixel size. So if you have a complementary disk image with, let's say, a resolution of 0.2 arcseconds, you want to set your pixel size to 20% of that. So 0.004 arcseconds. And then your image size, yeah, you kind of need to think how large is my disk going to be, how much large do I want to make my image. So essentially my default is to set that to 400 and set the cell to like sort of a quarter of the beam size. That will give you a reasonable looking image. But also there, sometimes you have to play a little bit with that. Like you have to try a few parameters before you find get the image that you're looking for. Then you have to define what it is that you want to do. So spec mode equals MFS means that you're going to clean continuum, so that it will merge everything together. But you can also set it to cube if you want to do line cleaning. I'm going to show examples. If you're doing line cleaning, you always have to set a reference frequency. Finally, the primary beam correction is smart to set it to true. So this is the correction that I mentioned in the beginning, that your sensitivity across your primary beam, so across your entire antenna dish, becomes your sensitivity becomes lower if you go further away. So you essentially do a correction for your noise levels throughout your image, that your noise levels are higher in the output. Okay, then there's this very important parameter that I mentioned before, the weighting. So weighting you can set to either natural, uniform, or bricks. And if you set it to bricks, then you have to set your robust parameter to a value between -2 and 2. That's for the different then your number of iterations, so this is how often you go through how many cleans you want to do. I always set it to a really large number, like 10,000 or 100,000. Usually I don't go that many steps, but just so that it gives me the possibility to go longer. And you always want to set interactive to equal to true in order to see what's happening during the clean. If you set it to false, it will just run by itself, but then you don't really notice what's happening, whether it's cleaning and the other direction. Okay, sorry, this thing should have been a little bit higher. So it should have been threshold rather than sigma. So threshold is essentially telling you how deep you want to clean. It's smart to set it to 3 times the noise level. The first time you do clean, you don't know yet what the noise level is, so then you just pick up, just set it at 0 millidensity. But then after you've kind of figured out this is my typical noise level, it's smart to keep it at the 3 sigma level so you don't clean deeper than that. Okay, so now we go for an example. So say that I've started my clean, I've set all my parameters, so this is the data set, my measurement set, this is my field, this is my data column, my image name, container I'm cleaning, image size, number of pixels, cell size, and weighting bricks with a robust 0.5, interactive is true, and number of iterations, like 10,000. So now this is my dirty image, and as you can see, there's a lot of crap around, but here's my central source. Now what you want to do is to set a mask around the part of the emission that you think belongs to your source, because it will use that to estimate these brightness points that are used for your clean model. And in the CASA logger, you can actually see what's happening. I suggest that we just go through that. So this is after we've done 100 iterations. 1,000 iterations. So we see that the counter is now at 9989. It started at 9999, and it does 100 iterations per 100 cycles per iteration. What we see now is that there's suddenly 2 sources, because we've cleaned deeper and deeper. And suddenly there's a second source that was not visible before because of the side lobes and noise. So now we want to make our mask a little bit larger by saying, okay, this is also a real source. And the mask is drawn by hand with one of these square or circle. Again, you will see that in the tutorial. So now we've done a number of additional iterations. Now we actually don't see any real signal anymore. All of that is left now in noise. So this is the right moment to stop, to click on the red button, and then it's going to save whatever it has done. This will be your clean image that is now, that you can then open separately. When we started with this dirty image, we thought that this was maybe a noise block, but as it turned out, that was actually real. And we can see that now in the final image. Again, this is going to be a lot more clear when we start. I already mentioned if you want to do line cleaning, you will have to set your spec mode to Q, and then you suddenly have to set a lot more parameters, because if you're doing line cleaning, you're cleaning something as functional velocity. So you have to define the number of channels, the start where all usually set it to -20, the width, so this is your velocity resolution that you want. Out frame equals LSRK, that's very important because this is, if you don't set that, then it's going to do weird things. This, again, is because of the Earth moving and the object moving, and like setting it to LSRK means that you correct for all of those movements, and that you really measure how this thing is moving with respect to itself. And then the rest frequency, this is the frequency of your okay? Then there is an option in in your clean. It's by it's the what the name is, sorry. It's not the option. Here we go. The deconvolver by default is set to Hogbo. So this is that cleaning algorithm that I've been talking about. Like collecting right point sources, assuming that that is your image, your model image. However, you can also set the deconvolver to something that's called multi-scale. Multi-scale is better in dealing with extended sources, so something that doesn't really describe as a number of point sources. For example, a prototype like this. So as what you see here is this kind of result. If you have an extended source and you clean it with Hogton, it's actually hard to get rid of that final sort of large-scale emission. The multi-scale algorithm, it's not going to try to fit like all the point sources, but something that is a bit more like a global structure, and then your residuals. So again, in prototech, you can try both and just see how it works. Okay, then an ALMA data set is usually ending with something called .ms. It's going to look like a folder in your directory structure. That is because inside that folder you get all these subfolders and subfiles. You don't want to mess with anything that is in that folder. The way to read in a measurement set is using the CASA software. So don't ever start playing or deleting files in here, because then the measurement set becomes corrupt and you cannot do anything with it. So it's just how the data is saved. Okay. So another very useful task in CASA is list ops. So list ops, where you set again this equals your measurement set. It tells you what is in my data. So I can, here I see the PI of the data, the project, something you can see here the dates that it's observed, and even the time, like the time steps where it has taken observations. You can see all the different fields. In this case, there's only one field in the array and the coordinates of that. Then the spectral windows with all the different frequencies. And then further below, you can actually see the names of all the antennas. So list ops is a way to get the basic information about your measurements. Plot-MS is another tool in CASA that can help you to inspect data before you start cleaning. So in Plot-MS, you can, for example, plot your data, the amplitude as a function of frequency. What we see now is that spectral line. So now we know immediately which channels contain continuous data and where the line is located. Making a plot in Plot-MS can be really slow. So what you usually want to do is average over the quantities that you're not plotting. So if you plot something like amplitude over frequency, you want to average over time and you want to average over all baselines. In this case, now we have a plot amplitude as a function of unit distance. That means that again we want to average over time, but now also average over all the spectral windows. So again, try a little bit with these options of averaging and how that looks like in Plot-MS. Finally, so you can plot against like one parameter against another parameter. But you can also, in another part of this tool, you can polarize by a third parameter. So in that way, you basically add a third dimension to your plot. Where, so for example, here we have our visibility data, and each antenna gets a different color. So say that you think you have some weird data that seems a little bit offset from the rest, and then you polarize that antenna and you see that it's all the same color. Well, maybe that whole antenna produces bad data, so you just want to flag it altogether. So also here, just play a little bit with that. So, yeah. yeah, then I already mentioned the data column. So this is something that's it's actually very confusing. I don't know why they made it like this. You have 3 different columns in a measurement set. You have data, corrected, and you have model. The model is something you don't have to worry about for now. Corrected is whenever you apply a calibration, the data gets copied into the corrected column when it is corrected. However, if you split out your corrected data afterwards, it ends up in the data column. So in practice, if you split out things several times, you always end up with your correct, your calibrated data in the data column. So that means you just want to check that in Polymath your plotted data about it is correct. Okay. Yeah, so data sets can be very large, and I tried to